in this lesson, we are going to discuss this problem. Draw the shear force and bending moment diagram for the following beam. Here you can see the cantilever beam supported by one end, the fixed support. And here you can see the linearly varying distributed load is acting. The intensity of the distributed load is vary. At this end, it is equal to 5 kN per meter. And this free end, that is equal to 2 kN per meter. The beam length is equal to 2 meters. Okay. For this problem, we are going to draw the shear force and bending moment diagram. Okay. First step, I am going to draw the free body diagram for the entire beam. Okay. So, let me draw the free body diagram for the entire beam. See the beam. AB, the length is equal to 2 meter. And this is subjected to a linearly varying distributed load. This is how distributed load is varying. Here at this end, the 2 kilonewton per meter, and at this end, the 5 kilonewton per meter. Then at this end, fixed support is acting. Let's take this one as RA. Let's take this moment as MA. Okay, this is the free body diagram for the entire beam. Okay, let's determine this RA and MA first. To determine this RA and MA, I am going to resolve the forces in a vertical direction. Here you can see the linearly varying distributed load. This area is a trapezoid. So then the resultant force is equal to the total area of this trapezoid. So RA minus the resultant also acting through the area centered of this trapezoid. So let me mark this resultant force. Let's take somewhere in here. R. Then what is the area of this trapezoid? That is equal to the addition of 5 plus 2 divided by 2 into the distance between the parallel line, that is equal to 0. So then the RA we are getting is equal to 7 kilonewton. RA is equal to 7 kilonewton. Then by taking the moment around this A point, I am going to take the moment around this A point. MA plus, so then the moment produced by this distributed load. To find the moment produced by the distributed load, I am going to divide this area into rectangular section and this triangular section. For the triangular section, the resultant, let's take the resultant produced by this triangular section area, let's take R1, rectangular section. Then for the triangle section, let's take R2. Then what is the moment produced by this area rectangular section? That is acting clockwise direction. So minus. So total area is equal to 2 into the height is equal to 2. Distance from the AN, this is acting in the middle of the rectangle. So that is equal to 1 meter. If you take the triangular section, again the minus, the clockwise moment. So that area is equal to half into 2 into height is equal to 3. Then the its resultant, R2 resultant acting through the area centered of this triangle. So distance from this AN, this is equal to 2 divided by 3 distance. So then we can simplify this equation. here equal to 0. Then MA is equal to 6 kilonewton kilonewton meter. 6 kilonewton meter. 6 kilonewton meter torque. Okay, then I'm going to obtain the shear force and bending moment equations. I'm going to section the beam somewhere, this kind of position, at the x distance from the AN. Let's take this distance as x. Okay. So then I'm going to draw the free body diagram for this separated beam part. Here the beam part. Let me mark the load acting on it. Okay. This is the distributed load acting. Then the shear force acting on this face, shear force. Here, let's take the bending moment, and this distance is equal to x. And moment, we have found that value is equal to 6, and force acting on the fixed support is equal to 7 kilonewton. Here 6 kilonewton meter. Okay, this is the free body diagram for the entire beam. Separated beam part. This is the free body diagram for this separated beam part. So then, let me separate this trapezoid area to a rectangular section and the triangular section. Okay. Then the height of this point. Here, this height is equal to 5. Then at the x distance. So here you can see the reduction of height for 2 meter length. The reduction of height is equal to 3. Then for the x distance, the reduction of height is equal to minus 3 divided by 2 into x. The reduction of height. So then this height is equal to 5 minus 3 divided by 2 into x. Okay. Okay, then so I'm going to write the equation for the shear force. By resolving the forces in vertical direction, I'm going to resolve the forces in vertical direction. Minus shear force. Here plus 7. Then the resultant force produced by this trapezoid area. Here the linearly varying distributed load up to x point. So how we are calculating the area? The addition of parallel line plus 5. Sorry, trapezoid is acting downward direction. Here it is minus 5 plus 5 minus 3 by 2 into x. Divided by 2 into this length into x. Okay, these are all the forces acting in a vertical direction, so equal to 0. Then by taking shear force into subject, we are getting by simplifying this equation, plus 3x divided by 4 minus 5x plus 7. And the shear force equation is equal to 0.75 x square minus 5x plus 7. This is the shear force equation. This is the shear force equation. Then shear force at x is equal to 0. What is the value? Shear force at x is equal to 0. The value is equal to 7. Shear force at x is equal 2. Addition. the value is equal to 0. Yes, shear force is a varying, shear force having the parabolic variation, having the minimum, because this coefficient is positive. So we need to find the minimum value and it's a symmetric axis. First, let's find the symmetric axis. The x symmetric axis minus b divided by 2a. Here we substitute the values, minus 5 divided by 2 into a, 0.75. This value is equal to 3.33 meters. At this point, this parabola having the symmetric axis, so then we can find the minimum as well. Shear force at 3.33. So by substituting this value in this equation, we can get the minimum value minus 1.348. Actually, this is out of the span of the beam, but we need this value when we are going to draw the shear force diagram. Okay, then let's find the bending moment. Okay, next I'm going to find the bending moment equation. To find the bending moment equation, let's take this point as O. So I'm going to take the moment around this O point. Okay. Then by taking the moment around this O point, bending moment, then we don't have any moment from the shear force. Here 6 plus 6 minus 7 into x. So then the moment produced by this distributed load, linear invariant distributed load, then I'm going to take this moment by dividing this total area to two areas, rectangular section and the triangular section. So what is the moment produced by this rectangular section? Let's take this is R1. R1, the distance to the R1 is equal to x divided by 2. Here, x divided by 2. Here, for this triangular section, let's take this value as R2. The resultant R2, the distance from the O point, that is equal to 2/3 of x. 2/3 of x. Okay. Then, first of all, let's find this moment produced by this rectangular section. The area plus x into this height, 5 minus 3 divided by 2 into x into distance x divided by 2. Okay. So then the moment produced by this force due to the triangular section, the triangular section area is equal half, here that is also positive, half into x into this height. This height is equal to 5 minus 3 divided by 2 into x. Then the distance from O point to this line of action of the R2, 2/3 of x is equal to 0. Okay, this is the equation. By simplifying this equation, we can get the equation for the bending moment. Okay, so I will write this equation. The bending moment equation is equal to, by simplifying this equation, 0.25 x into cube minus 2.5 x into square plus 7x minus 6. This is the bending moment equation. So when you're going to draw the bending moment diagram, we need the bending moment at x is equal 0 value. If you substitute the 0 in this equation, we are getting the minus 6 kilonewton meter. Then the bending moment at x is equal 2. If we substitute the x is equal 2 in this equation, we are getting the value 0. And also you can see it's a cubic function. So here we are going to calculate the maximum and minimum points. If we derivate this equation, the bending moment equation with respect to x, actually in here we are getting the shear force equation, that is equal to 0.75 x square minus 5x plus 7. At the maximum or minimum, this expression should equal to 0. So let's find the maximum and minimum points. 0.75 x square minus 5x plus 7. Then the root of this equation, how we find the root of this equation? We can use the calculators x1 and x2 to find the root of this equation. The roots are 2, 4.66. These are the two roots. So then at 2 and 4.66, this equation is a bending moment equation having the maximum and minimum values. So here the 4.66 is out from the span of the beam. So I'm interested about this 2. So let me find the whether this at 2 the bending moment having the maximum or minimum value. So to determine that one, I'm going to take the second derivative of the bending moment. If you take the second derivative of the bending moment equation, the dx square, we are getting 1.5x minus 5. If you substitute the x is equal 2 in this equation, we are getting the negative value. It is equal to negative value. If x is equal to. So at x is equal to, we are in the maximum value is equal to 0. So then we are having all the data to draw the shear force and bending moment diagram. Okay, let's see how to draw the shear force and bending moment diagram for this problem. Okay, in here I have listed all the equations so far we obtained. The shear force equation, shear force x is equal 0, the value is equal 7. Shear force x is equal 2, the value is equal 0. The parabolic variation, the symmetric axis 1.34, at 3.33. At this 3.33, it's having the minimum value 1.348. So then this is the bending moment equation. At bending moment at x is equal 0, that is value is equal to minus 6. Bending moment at x is equal to the 0. The bending moment maximized at 0.2, that maximum value is equal to 0. Okay, now we are ready to draw the shear force and bending moment diagram. Okay, let's start from the shear force. Shear force at x is equal to 0, that the value is equal to 7, somewhere in here. Then shear force at x is equal to, the value is equal to 0. Then the shear force at x is equal to 3.3. 3.3 means somewhere in this kind of position. Here is a 2 meter length. Yeah. Here this length is equal to 2 meter. 2 meter. Somewhere in here, that value is equal to 3.3. That value is equal to 3.3. Somewhere in here. Okay. Let me draw the shear force diagram. This is the shear force diagram. This is how shear force is varying throughout the length of the beam. Okay, next I am going to draw the bending moment diagram. This is the variation. The bending moment at x is equal to 0, that the value is equal to minus 6. Okay, let me mark this one value also. 7. Okay. minus 6. Then bending moment at x is equal to value is equal to 0. Then this is the maximum value. This is the maximum value. So sorry, this is one of the maximum. Yeah, this is the maximum value. So the equation like this. Okay, this is how we are drawing a shear force and bending moment diagram for this kind of beam. Here you can see this intensity of the distributed load is linearly varying from 5 kilonewton to 2 kilonewton. In this situation, this is how we are drawing the shear force and bending moment diagram. Okay, thank you. See you next time.